for our second talk. Lewis is going to talk about packing by scheduling using constraint programming to solve a complex 2D cutting stock problem.
Yeah. Thank you so much. So, hello everyone. My name is Lewis, and today I'll be presenting our paper, Packing by Scheduling, using constraint programming to solve a complex two-dimensional cutting stock problem. This work was performed at the Toronto Intelligent Engineering Laboratory at the University of Toronto, supervised by Professor Christopher Beck, and our industrial collaborator is Kinaxis. So today we'll be going over 4 main parts. First, I'll be providing a description of our problem. Then we'll be moving on to our primary contribution, the single resource constraint programming model. And then I'll talk about some of the alternative approaches that we've investigated. And finally, we'll present the results. So first, what is our problem? Well, our problem lies in the rolled metal industry, where manufacturers need to cut large cylindrical coils of stock material. For example, you have aluminum, you have paper, into smaller coils, so that they can fulfill client orders. And abstracting away from this industrial application, what we have here is a two-dimensional cutting stock problem with industry-specific requirements. And specifically, we can break down the requirements into 3 main components. Those related to stocks, those related to orders, and those related to the cutting process. And in the next couple of slides, I'll go over them one by one. So first, a stock. A stock is essentially just a large rectangular sheet of material that can be cut into smaller pieces. We're given a finite set of stocks, and for each stock, we have a fixed width and a fixed length. In fact, in the remainder of the presentation, what you'll see is that for stock material, I'll have the length in the horizontal axis, and I'll have the width on the vertical axis, just to keep it consistent. Finally, in our problem, the stock length, right over here, are all the same. So we're assuming the length of the stocks are all the same in our problem. Next, what is an order? Well, an order is just a set of smaller rectangular items that client can request. And for each set of order, for each order, it's comprised of smaller items. Each item has a fixed width and the length that's flexible within the interval. Furthermore, the total summation of the area of the items needs to be within some interval that the client requests. So now that we have a definition of what is a stock, we know what is an order, how can we relate the two? And then we relate the two by defining the cutting process. So industrial cutters often use something called the guillotine cut, or for the French audience here, guillotine, à la française. The guillotine cut is essentially the type of cut that runs from one edge of the underlying object all the way to the other edge. In our problem here, we're dealing with a specific kind of guillotine cut, the 2-stage guillotine cuts, which is essentially just 2 sets of guillotine cuts that needs to be made sequentially. The first stage will be executed widthwise, so parallel to the width. And the second stage cuts will be made lengthwise, so parallel to the length. Here in the figure is shown, oh, what did I do? I did that. Okay, so as you can see in the figure here, on your right-hand side rather, this is a valid valid cutting pattern for 2-stage guillotine cuts. And after the first stage cuts are made, as you can see by this vertical here, we will obtain 2 vertical strips after the first stage cuts are executed. And on each of these strips, we can execute the horizontal second stage cuts to obtain these little smaller rectangles, which are essentially items that are then can be used to fulfill client orders. To further stress this point, we provide some examples of invalid guillotine cut pattern. So again, on your left-hand side here, that's what I showed you earlier. That's a valid 2-stage guillotine cut pattern. In the middle, this is an invalid guillotine cutting pattern. That's because the cut, as you can see here, stops right in the middle of the stock. It doesn't run from one edge all the way to the other. Finally, on the right-hand side here, this is a valid 3-stage guillotine cut pattern, but not a valid 2-stage guillotine cut pattern. And the reason for that is because of this little cut over here, this cut that's highlighted in red, that little cut needs to be executed with the 3rd stage of guillotine cuts. And finally, in terms of cutting process, we have one additional requirement, and that is industrial cutters often have a limit on the maximum number of 2nd stage cuts. So in other words, we have a limit on the maximum number of little items that can be obtainable from executing one set of 2nd stage cut on a vertical strip. And we denote that using eta, so that's the limit. So in total, in our paper, we present this problem, the 2-stage cutting stock problem with flexible length and flexible demand, abbreviated as 2SCSP-FF. And it's characterized by flexible item length and flexible item demand. It's characterized by guillotine cuts that must be executed in 2 stages. And it's characterized by a maximum number of 2nd stage cuts. And their goal is to minimize the waste, which is essentially this grayed out area. So our primary contribution is the single resource constraint programming model, which poses our problem as a scheduling one. In particular, the single resource scheduling model uses CP scheduling tools, so constraint programming scheduling tools that include optional interval variables, state functions, and pulse and cumulative functions. And in the next couple of slides, I'll briefly talk about what each of these are. So first, optional interval variables. Optional interval variable is a type of variable that's whose value is either some semi-open interval on some time horizon, or a special value indicating absence. Each interval variable, optional interval variable, is typically defined by a start time, an end time, and some duration. That's the duration of the interval. And example usage of this typically is jobs or operations in the job shop scheduling problem, for example. A state function is a variable whose value is essentially some non-overlapping, is essentially a set of non-overlapping intervals. And sometimes we can even associate integer value to represent the states. And the idea is that the state, we can essentially use constraints to associate the interval variables that I described earlier to the states in a state function. Finally, we have pulses and cumulative functions, which are typically used to profile some sort of resource usage over time. In particular, pulses is an expression that indicates an interval's contribution towards a resource over time. And an example of that, if you want to visualize it graphically, essentially this rectangular function, essentially this is just this rectangular function. And cumulative functions is similarly an expression that represents a summation of all of these individual contributions over time. So in other words, the cumulative function, visualized graphically, is just the summation of all of these rectangular functions, as you can see to your right, to your left. Okay, so now armed with the knowledge of CP scheduling modeling tools, we can now delve into actual model. Our model is comprised of 3 main components. We have a state function for, we have a unified domain of stock lengths. We have state function representing the cuts, and we have cumulative functions tracking widthwise resources. So first, our model uses something called a single resource transformation, as as we have kind of hinted at with the name of our model. The single resource transformation is a recently proposed CP scheduling technique to solve where the original paper, they solved a capacity and time constraint routing problem. And the transformation is essentially, let's think about when you have a vehicle routing problem, you have vehicles, we have the routes, right? And each route is a different vehicle. The transformation essentially just merges all these resources together. So you have, instead of 3 separate vehicles, for example, you have one big long vehicle, if you will. And the idea is that we can apply constraints over the entire horizon instead of over each individual resource. And the hope is, of course, this will provide stronger inference And in their paper, they showed that this transformation yielded a significant computational advantage over traditional CP modeling, over traditional CP models, in particular with regards to the size of the model, as well as the performance of, as well as solution quality. So in our paper, we adapt this single resource transformation to our problem. In particular, if you remember from the previous slide, we have vehicles that are stacked together, right? That are concatenated together. Instead of vehicles, what we have here are the length of the stalks. We're concatenating the length of stalks to form one single unified horizon. And then on this horizon, we're going to define for each item of order an interval variable representing its lengthwise coordinates. In particular, the duration of the interval variable is allowed to be flexible within some range, and this can be accomplished natively in CP scheduling solvers. Now, one issue that you might notice is that over here, you have items that actually span two adjacent stalks. And that's no good. We can't cut an item from two separate stalks, right? So what we do is that we insert a dummy unit of infeasible regions in between the adjacent stalks. And we use constraints, the global extent constraint in particular, to remove these infeasible regions away from the domain of the item interval variables. Thus, the item interval variable has to be either within one stalk or another. Then we also declare another set of interval variables for each stalk. An idea that we need to declare these to track essentially if a stalk is used or not. Now, Guillotine functions. So Guillotine cuts. Guillotine cuts turns out can in fact be modeled using state functions. And the key observation here is that items, the lengthwise coordinates of the items, if you think about a feasible solution, can never overlap if they're in different horizontal if they're in different vertical strips. In other words, if we project the lengthwise coordinates of all of these items onto this unified horizon, we obtain a series of non-overlapping intervals, which is precisely the definition of a state function. We can use constraints to essentially align the coordinates of the item interval variables with the states in the state function. And finally, and as a result of that, items can only be on the same vertical strip if they belong to the same interval in the state function, same state interval in the state function. Finally, we still need to somehow account for the width of the stalks, as well as the maximum number on the second stage cuts. What we notice is that both of these are essentially widthwise resources, especially if you think about it over an entire horizon. There are resources that change over this horizon. In other words, we can model this using cumulative functions. So for example, for the width of the stalks, we're generating a pulse in the positive direction for each stalk, representing the available width of that stalk. Similarly, for each item, we're generating a pulse, but this time in a negative direction, to indicate that the item actually depletes the width of the stalk. In terms of the number of second stage cuts, we're generating a unit pulse in a positive direction for each item, so that as long as the total summation of all of these pulses, in other words, the cumulative function doesn't exceed the maximum limit, we're obtaining a satisfying solution. So in other words, our single resource constraint programming model, by modeling the unified lengthwise horizon, by using a state function to represent the Guillotine cuts, and by using cumulative functions to represent the widthwise resources, we're able to represent the entire problem. Now, some other approaches that we investigated, we looked at a counting-based constraint programming model that essentially count the number of items belonging to an order present on a vertical level of a stalk. We looked at a stalk-based constraint programming model, which essentially matches the possible little rectangle on each vertical strip to the index of the order. We also looked at a mixed integer linear model that essentially uses binary variables to assign possible items. on vertical levels to orders. And we looked at a first fit based heuristic that packs items of orders into stocks iteratively on the first fit basis. In fact, beyond these 4 models in the paper, we also mentioned some other approaches. We mentioned a CP model that uses the global constraint pack, as well as another MIP model. And we found that these 2 models, their performance were inferior to the ones that are shown here. So we didn't present the full formulation of the models in the paper. Okay, so now let's dig into the results. So we're experimenting with 50 generated instances and 4 industrial instances provided by our industrial partner. We're use Cplex and CP Optimizer from IBM Cplex Optimization Studio, accessed via the Python docplex library. Each model is given 16 gigabytes of RAM, 1 hour time limit, and all experiments are single-threaded using default search and inference settings. So first, we look at the size of the models. In the left-hand column here, we show the memory size of the model before the search has started. So before the CP search or MIP search. And we essentially observe an order of magnitude advantage of that our single resource CP model has over all the other approaches. And in particular, if you look at the largest generated instance here, 64 orders, 128 stocks. The single resource model requires only about 20 megabytes of memory, whereas the second largest requires over 100 megabytes. The single resource model also uses significantly fewer variables and constraints, as you can see on the right, in the middle and the right-hand column here. And in fact, the plots, they're actually log scale, so the distances appear larger than a scene. Accordingly, the single resource model is the only model-based approach to find a feasible solution to all instances tested. Interestingly, the single resource constraint programming model also requires very little time to reach the first feasible solution as well. Now, looking at the final solution quality, we see that for small instances, the mixed integer program does in fact perform the best. But as the size of the instances scale up, the MIP struggles with tractability. In comparison, the single resource model found competitive solutions for small instances and found very high quality solutions for the large instances as well. In fact, making it the only viable model-based approach to use for the industrial use cases. So in conclusion, we present a single resource constraint programming model, and we show that it outperformed alternative integer-based CP models, MIP models, and the heuristic, especially on large generated industrial instances. Finally, we believe that the flexibility of constraint programming scheduling tools can be used to provide a very promising approach to tackle complex real-world problems beyond just the scheduling ones. Thank you very much for listening.
Thanks very much. Time for questions.
Thank you, very nice for that. Can you rotate the orders?
So no, we're not allowing the rotation, the orientation of the order at all.
Why?
Well, essentially, if you so what happens in the actual real world industries is that the stocks are quite large in terms of length, and the items that needs to be cut out of it are also very large. So in fact, if you rotate it, it wouldn't fit. So
it's also the case that sometimes the underlying material have a grain.
Yes.
Right, and so that grain has to be in the right orientation.
You mentioned you computed feasible solutions, but you also mentioned that you have waste. So you want to minimize the waste. What means feasible? Minimal solutions according to waste, or any solution?
Right. So by what I mean by feasible is just any solution that satisfies the constraints in our problem.
Okay, with this restriction you mentioned.
Exactly.
Okay, but not minimizing the waste.
Not necessarily minimizing the waste. Yes. So I think just to add on to that, essentially, a lot of the other models, it takes a long time to just compute to just define a solution that satisfies everything, right? I think that's what we were trying to show.
Yeah, but it becomes even harder, the problem if you do minimization, yeah, of the waste.
Yes.
But to be clear, we are minimizing waste.
We are
What we're
We are
just showing is the first time we get a feasible solution.
Okay.
But the model minimizes waste.
Yes.
You have many orders that are exactly the same.
Many
orders.
Many orders that are exactly the same. So if they're the same, so sometimes not a lot, because essentially if you think about the lengthwise intervals, right, they're sometimes a little different. You do get orders that perhaps have similar range of total areas, for example, or similar width, but I think there's some variability in there. Yes.
One question.
Use this one sort of interval to just separate the stock pieces, right? Or one width interval to separate the stock pieces. Couldn't you use a 0 width interval and use a strict non-overlap to do the same thing?
Yes.
Does that exist in CPAIOR?
Yes, I think it does. Hold on, you're saying.
I guess it doesn't make much difference, but it would make your arithmetic slightly easier.
True. Maybe that's something I think I have to think about. Yeah, maybe.
Right. Thank you very much.
Okay, thank you so much.